Hi friends. Okay, so now we will discuss the carbon monoxide molecular orbital diagram. So for that, first of all, let us see what all atoms are involved. So carbon and oxygen is involved. Okay, what is the number of valence electrons? Let us see for each atom. 1s2, 2s2 and 2p2. For oxygen, it is 1s2, 2s2 and 2p4. Okay, so the valence electrons are 4 and 2, here 2 and 2. So valence electrons here is 4 and 2 6, 2 and 2 4. So total number of valence electrons, so these 10 electrons we have to accommodate in the molecular orbitals. We can easily accommodate that. We know how to draw. Okay, let us see by our simple convention what we need to do. So if we try to draw an energy level diagram, so now we have different atoms, so let us label them as carbon, atomic orbitals of carbon and atomic orbitals of oxygen, right? Okay, now as we had seen in the previous section that what are the important rules for drawing these. So first of all, which one is the more electronegative element? Obviously oxygen is the more electronegative element and its atomic orbitals should be located at a lower energy than the atomic orbitals of the carbon. So let us locate them like this. Okay, and then again 2s. Okay, now carbon will be at a higher level. So this is where the difference comes while drawing the molecular orbital picture of the heteronuclear molecules, and the 2p of carbon will be high above the 2p of oxygen, like this. Now by normal convention we would have drawn like this, that 2s and 2s will give rise to sigma 2s, although there will be above and below, that means it will be quite an unsymmetrical picture. Like this we would have drawn the p orbitals giving rise to px, py and sigma 2pz, like that we would have drawn. But now one difference comes here also. There will be you can draw it like that, but actually the carbon monoxide molecule, in this molecule what happens, there is uh, sp mixing is also there. So while we discuss the molecular orbital picture, the mention of sp mixing is important, which gives rise to the kind of hybridized orbitals. So based on hybridization we will discuss it, and it becomes quite a little bit complicated. So sp mixing is there, we had seen till nitrogen. Sp mixing is quite very much possible because the energy difference between the 2s and 2p orbitals is less. This we had discussed. So sp mixing is possible in case of carbon, also in case of oxygen, but lesser to a lesser extent than carbon, right? So carbon sp mixing is there. So let's discuss. So if there is sp mixing in case of carbon, that means 2s and 2pz. Why 2s and 2pz will mix? Because they are symmetrically and energetically similar. 2s and 2pz is like this, right? So that is why they can intermix, giving rise to a new kind of orbital. So let us name this orbital as 2spz, like this kind of hybridized orbital. So 2spz, so this is atomic orbital, please keep in mind that we are discussing now. 2s and 2p pure orbitals, they hybridize, they mix, intermix and give rise to a new kind of atomic orbital, that is the 2spz. And 2spz also has a high energy, right? 2spz and a low energy 2spz, right? The high energy will be having more characteristics of the pz orbital, and low energy will be having more characteristic of 2s, 2pz pure and 2s pure orbital, right? So this pure orbital, what is the meaning of this more characteristic? That means it will be energetically, the high energy 2spz atomic orbital will be energetically more near to the 2pz orbital, atomic orbital, and this will be energetically near to the pure 2s atomic orbital, like this. Okay, so up to now, hope this is clear. So let's repeat again. So there is sp mixing in case of carbon, right? Because the 2s and the 2pz atomic orbitals are energetically close enough, and they are symmetrically also comparable. So this gives rise to the sp mixing in case of carbon, and the sp mixing results into the formation of a 2spz hybridized atomic orbital. And these 2spz atomic orbitals, one is high energy, another is low energy. Higher energy is characteristically more towards the 2pz pure atomic orbital, and that is why it should be located near to the 2pz atomic orbital. Similarly, the low energy is characteristically more towards the 2s, and it should be also located, that is why, towards the pure 2s atomic orbital. So up to this hope this is clear. So now I will draw it here only, and then we'll draw a fresh diagram. So what happens? So S and P, that the pure S and P, they mix, and the lower energy one should be located near to the this one. So 2spz low energy should be located near to the 2s pure orbital, and the high energy should be located near to the 2p orbital, right? Like this. Okay, and then as usual we have 2p orbital. Hope you understood this. There's the new hybridized orbital will be 2spz orbitals. One is located near to the 2s, another is located near to the 2p, right? So carbon gives us the hybridized 2spz orbitals, which are 2 in numbers, like this. Okay, now this kind of mixing, sp mixing, is also there in oxygen, right? And oxygen also gives low energy and high energy 2spz and 2spz orbitals, atomic orbitals. Oxygen gives, but that oxygen is having a low intensity or a low probability of this mixing, although there is mixing, but that is low because the 2s and 2p atomic orbitals, the energy difference between them is quite high, but still there is mixing, right? Okay, so this also gives, and then we have this more 2spz and also 2spz of oxygen, right? Okay, so we have 2spz, 2spz. So these two for carbon and 2 for oxygen. So this is how we get our hybridized atomic orbitals. Okay, and the 2p remains the same. Okay, there is no change in 2p. Only what change we will have, because since this pz orbital is involved in hybridization, right? So that is why we will have only two 2p orbitals, right? Because one pz from the pure p is involved in hybridization. So we will have only 2p orbitals. So now we will draw the molecular orbital picture of the carbon monoxide molecule based on hybridization.